Hello and welcome. This is Electricity and Magnetism, Part 5. Today I'm going to talk about capacitors. Capacitors are tools that are used to hold charge. You already saw a certain type of capacitor which is made of parallel plates. Suppose a rectangular shaped metal right next to an identical shaped conductor like this, and somehow you've managed to put charge on these two plates. So we have, let's say, positive charges on the left hand side, and on the right hand side we have negative charges. As it is in the case of conductors, when you reach equilibrium, you will have equal number of positive charges on one side and the other side. So the amount of charge is the same. And also these are uniformly spread. So let's call this Q and this negative Q. Now the electric field, due to this system of or configuration of charges, is from the positive to the negative, as you know. These are pretty much parallel, except for maybe when you reach early to the end, they start curving like this. Well, we're not interested in that yet. Now you may say, what about the regions here and there? Well, that's where E is so weak that we take it to be equal to 0. So if you're wondering why that is the case, imagine you have the positive charge on the left hand side, which would normally create electric field like this, if that was the only plate. Now by adding the other plate with negative charges, we have electric field toward the plate, which is fine between the plates, that agrees with the other field, but right here, if it's going to be to the right, that's going to cancel the other field. Okay, using the same principle, we can extend these green lines to this side, which will cancel those. Okay, so that could be an argument you can use to see why electric field is supposed to be 0. In real life, there may be some field, but we're going to ignore it in this example. Okay, just holding two charges like this. And the positive and negative charges like to be around each other. Okay, so if you just leave those plates like this, those charges will stay there because there will be a force between them, and they're going to occupy the plates. So when you hold these two plates with the charges on them, you have a potential difference between them. Obviously, the plate on the left, let's call it L on the left, and the one on the right. The one on the left has a higher potential, VL greater than VR. Remember, electric field goes from high potential to a lower potential. So the potential difference when these plates are all D apart, let's say, so delta V, that is VL minus VR. Call it delta VLR if you like, just a shorthand for VL minus VR. All right, so the charge is related to the plate size. Okay, I mean, greater the plate, greater the charge it can hold. Also, the separation between the plates, that will play a role in how much charge you can keep on those plates, okay? The surface area and the separation between the plates. So let's call the surface area A. The area of the plates is A. Now let's do this. Let's find the electric field first using Gauss's law. To do that, you just have to consider some surface here, a closed surface, like a pillbox, like a cylindrical surface of some area, call it A tilde. A tilde is the area of the cylinder. This A is the area of the plate. So what does Gauss's law say? This integral E dot dA over the closed surface, which is the cylinder, will be equal to the charge enclosed divided by epsilon 0. Okay, that's one way of finding the electric field. So I think I did this example before. I'm not going to spend too much time on it. You know what's happening here. From the area, you will have A tilde. That's the area. Only right-hand side of the cylinder counts here. That's our integral. Now, what about the charge enclosed? We got to know the density, charge density, divide the total charge Q by total area. That'll give you a density. So multiply that density by the area on the plate, which is the cross section between that cylinder and the plate right here. That's also A tilde, but that's how much charge we have there. So sigma times A tilde is the charge contained in that blue shaded region divided by epsilon 0, and you can get rid of the area, and E is equal to sigma over epsilon 0. You can either use Gauss's law like this, or you can go back to the calculation of an electric field of a disk. Find the expression for that, and then take the limit when you're so close to the disk that it looks like infinite. So in that approximation, you will get the exact same expression, sigma over epsilon 0 for a conductor. All right, so I'm going to use this to find the potential difference, delta V. That's VL minus VR. Therefore, it is from left to right, whatever coordinate system you're using. Those are 2 points there. E dot dl. dl is the displacement along the electric field. They go in parallel. dl and E are parallel. Therefore, this integral doesn't have any cosine theta, or theta is 0. It's just 1. The integral just becomes, since E is uniform, meaning a constant, it just is E times D. Okay, that's your integral. E times D. All right, good. We found the potential. Now, what about the total charge Q? How is total charge Q related to the potential, for instance? Like if we keep the plates where they are, is it possible to add more charges on these 2 plates? The answer is yes. If you do that, what will change? Well, sigma will change. Sigma will increase. If sigma increases, electric field will increase. If electric field increases, the potential difference between the plates will also increase. Okay, so greater the charge, greater the potential difference. These 2 are proportional to each other. Delta V and the charge are proportional to each other. And that's a linear relationship. If I double the charge, I'm doubling the potential difference. So why don't I come up with a constant which would help me to write this proportionality as an equality, right? So that's what we call capacitance. Capacitance. So we're going to write this charge as this constant, which I'm going to call C, times delta V. So C will be defined as charge per potential, charge divided by potential difference, capacitance. All right? So the capacitance of a given capacitor is actually a function of the geometry of the system. Yes, it is equal to Q over delta V, but capacitance itself can be found directly from the geometry. Why is that? Well, let's try. So we have electric field here, E times D, that is delta V, right? So this is equal to E times D, and this is Q. Now let's write E as sigma over epsilon 0. And what is sigma? Sigma is Q over area. Q over area divided by epsilon 0 and then multiplied by D. So if I get rid of the charge, now I have an expression which is just in terms of the physical dimensions of the plate, the area divided by separation of the two plates times epsilon 0. All right. So what about the units that we have here? So let's think about it. We can use any of the equations here to find units. This is measured in farads. But farads is a derived unit. So that will be equal to coulombs. All right, we have coulombs here. This is in meters, and electric field is in newtons per meters, right? If you remember from the basic force law, F equals Q times E, the unit of electric field is newtons per coulombs. Oh, sorry, I meant coulombs, not meters. Newtons per coulombs. Sorry. Newtons per coulombs. So 1 farad will be equal to coulomb, 1 coulomb squared per Newton meters. That's what's equivalent to. There are other ways to write it too, like, okay, let's see. The force equation from Coulomb's law was 1 over 4 pi epsilon 0, Q1 times Q2 divided by R squared. So what we have here is newtons. Now we have here Coulomb squared divided by meter squared. So the unit of the electric constant will be Newton meter squared per Coulomb squared. Now this will be the unit of also 1 over epsilon 0, which I have here. So the epsilon 0, then I will have units of C squared, Coulomb squared over Newton meter squared, and then I have A over D meter squared divided by meters. Again, I get the same thing. Coulomb squared per Newton meters. Or use this here. Coulombs is the unit for charge. Volts is the unit for potential difference. So 1 farad is equal to 1 coulomb per volt. Okay, so that's called capacitance. And for a parallel plate, capacitor is just equal to the surface area times epsilon 0 divided by D. So closer the plates, greater the capacitance. It can hold more charge. Greater the surface area, greater the amount of charge it can hold. Okay. What about other types of capacitors? Do we always have a parallel plate? Like what about the ones that we use in circuits, right? In your phone, there are capacitors, but you don't find parallel plate capacitors in your radios and phones and TVs. So there must be other types. Well, one way is actually to do this is you can take a very thin, like an aluminum foil, right? A really thin film, a conducting film though, and then you can take another one just like that, but you don't want to touch each other. So you place something else in between, maybe a piece of paper. Paper is an insulator, right? Put a paper here. It's a long one, right? I mean, this is the length on this side, dimensions, width, let's say, and this is L. And L is usually greater than the width. You put them together, then you start rolling it. When you roll it, you end up with a cylinder. And you solder wires to these, this one, and then that one, which will be here and there. There you have it, a very small capacitor. That's one way of doing it. So you may have different geometries. It doesn't have to be really parallel plates, although it comes down to two surfaces which are kind of parallel to each other in practice. Another example would be maybe a spherical capacitor. So let's say you have this conducting sphere of radius A, and then you have another sphere around it, which is of radius B. And you place a positive charge on the inner sphere, positive Q, and then you will have a negative charge right here. Okay, now the outer sphere actually may have a thickness, right? I didn't draw it, but no matter how thin it is, it will have some thickness. So if that's the case, then these negative charges are on the inner side of the outer surface. So on the outside, we'll have again positive charges. If initially the outer shell did not have any charge, if it was neutral, the electrons will rearrange themselves so that they'll be on the inner side, which will leave the outside of the outer sphere as positive. So the net charge will still be 0. Let's not worry about it, okay? Let's not worry about it. Let's just find the electric field first between the two, because this will be my capacitor now. So consider a sphere of radius r. That will be your Gaussian surface. On that surface, this integral, not dl, dA, should be equal to the total charge inside, which is Q, divided by epsilon 0. Now using spherical symmetry, this integral is nothing but the electric field times area of that Gaussian surface, which is 4 pi r squared. So 4 pi r squared times E is equal to Q times Q over epsilon 0. Therefore, the electric field as a function of the radius is Q over 4 pi epsilon 0 r squared, just like a point charge. So I can now integrate to find the potential difference between the two spheres, VA minus VB, or delta VAB, is equal to an integral from A to B E dot dl. dl is the displacement, which is radially outward in this case. So right there, that is my dl vector. Electric field is also from positive to negative, which is parallel to dl. So I simply have this from A to B. E is Q over 4 pi epsilon 0 r squared, and dl is nothing but dr. So this integral will give me negative Q divided by 4 pi epsilon 0 1 over r. The limits are A and B, or negative 4 pi epsilon 0 1 over B minus 1 over A. This is my delta V. You may write it as Q over 4 pi epsilon 0 B minus A divided by BA. Okay, I got the negative in the front. So that is the potential difference, which is positive, as I expected, because VA is greater than VB. Good, that's the potential difference. What am I going to do this? I'm going to use it in this expression. Capacitance times the potential difference will give me the charge, right? So Q over 4 pi epsilon 0 times B minus A over BA times C. If you get rid of Q's, this will give you the capacitance in terms of the dimensions of this configuration. So 4 pi epsilon 0 BA divided by B minus A. Okay, the capacitance of A. System of two spheres which share the same center. Let me do another one. How about concentric cylinders? An inner cylinder, let's say this is length L with a radius A, or RA, doesn't matter. And then an outer cylinder, same length, which is L. Okay, they are parallel. So do I need to redraw that? Maybe I should get rid of this side, try to do a better job. Yeah, something like this. And the radius of the outer cylinder will be B. Okay, so I place positive charges in the inner cylinder, and this will be negative, just like the previous example. So the resulting electric field will be from positive to negative, radially outward. And I have a cylindrical symmetry, meaning the value of electric field is independent of the angle As long as you keep your distance the same from the center, the result will be the same. So let's find electric field again by considering a Gaussian surface, which is also a cylinder of radius r and length little l, let's say. So the Gaussian law is E dot dA is equal to Q enclosed divided by epsilon 0. Now the total charge is Q, negative Q here and positive Q in the inside. But how much charge do I have here? Only inside the Gaussian surface. How much charge do I have here? To find that, I need to multiply the length of the Gaussian surface by a charge density, a linear charge density, which would be equal to total charge divided by total length. That's my charge density. Charge density times the length of the Gaussian surface will give me the charge contained in that Gaussian surface. Divide this by epsilon 0. And on the left-hand side, the integral will be E times 2 pi r times L. So you will get to those L's like this, they will cancel, and then the electric field will be equal to Q divided by L 2 pi r epsilon 0. Let's give this guy a name. Lambda is equal to Q divided by L. Therefore, electric field is equal to lambda divided by 2 pi epsilon 0 divided by r. So the potential difference, delta V, then, will be the integral from A to B, lambda 2 pi epsilon 0 r dr, or lambda over 2 pi epsilon 0, the natural logarithm of B over A. If you carry out the integral, that's what you get. So remember, the charge is equal to capacitance times delta V. So I'm going to find the capacitance of this cylinder, or cylindrical capacitor, which is L meters long. All right, the length is L. A, B, and L are the physical dimensions of this capacitor, and they will matter in determining what the capacitance is. All right, so the total charge here is on the left-hand side is equal to C times, now we can plug in Q over L again, Q over L divided by 2 pi epsilon 0 ln B over A. All right, so Q's cancel. If you solve for capacitance, you'll get 2 pi epsilon 0 divided by L ln B over A. Okay, so if L is greater, the capacitance will go. Okay, well, I think I made a mistake here. Yeah, it's going to be times L. Sorry, this is times L. Apologize. So, right, we have Q over L. So L is in the denominator. When you solve for C, L is in the numerator. So greater the length, greater the capacitance of a cable. All right, some things this is not desirable sometimes. Say this is your signal cable from your TV to your cable box, or from your box to your projector. Okay, longer the cable, greater the charge. So you may not want to have long cables if you don't want noise in your signal, for instance. And what about the denominator? Logarithm of b over a. Now, if b gets closer to a, then the denominator will be smaller, which will make the capacitance greater. Okay, so this is our formula for capacitance of a cylindrical capacitor. All right, so what if we have more than one capacitor? What happens then? So let's say we have two. One capacitor here, and then another one. See, they don't have to have the same area. I can make this bigger. Different kind of capacitor, maybe different separation as well. They don't have to be the same, but I'm using wires to connect them. And let's say initially I have some charges here. And the reason I have charges is I'm holding the system. Maybe I'm connecting it to a battery. Therefore, I'm going to have some potential difference across these ends. Let's name these A, B, C. These are nodes or points on the wires. So I have a non-zero potential between these two. Delta V. Okay, so delta V or delta VAC. Now, if I have charges on this system, and let's assume that A has a higher potential, so VA is greater than VC, and point B is in between the two. If that is the case, this means I have positive charges right here. Okay, so positive Q. And this will be negative. Negative Q. Now this system will carry this much charge, and these two charges, no matter how different the capacitors are, will be the same. And here's the idea. Now initially in the middle, there was no charge. But because now I have a potential across points A and C, and I have charge in the system, on the left-hand side, if this is positive, the other side will be automatically negative because the charges will flow in that direction. They'll be attracted by the positive charges. And the amount of negative charges you will have on this plate will be exactly Q in magnitude. So positive Q and negative Q. If the negative charges over there, this will be automatically the positive charges on this plate, and they will be exactly equal to positive Q. So if you add these up, you'll get 0, which was the original charge. There was no charge in the beginning. It was neutral. Okay, so by adding these two plates and sandwiching that middle part from right and left, we're not really adding any charge. That part is isolated from its surroundings. That's why these two capacitors, no matter how different they look, should hold the same charge when the ends are applied to a potential difference, or if you keep those ends at different potentials. Okay, that's a very important point. So we're going to call this a series connection. Two capacitors connected in series. This type of connection is called in series, and whenever you have this, there will be only one charge. Q are the same on capacitors in series. Remember, the dimensions were different. Maybe this is equal to D1. This is D2. This has a surface area equal to A1. This is a surface area equal to A2, right? I already know how to calculate the capacitance. If you remember from the very beginning, the capacitance of these parallel plate capacitors will be equal to, for instance, A1 times epsilon 0 divided by D1. You can find the capacitance of the one on the right. That will be A2 times epsilon 0 over D2, etc. So if the charges are the same, though, if the charges are the same, I can write this charge is equal to this capacitance times the potential difference across the plates. So from A to B, I'm going to call it VAB. All right, just like I named VAC. So here's what I did. Delta VAC is VA minus BC. So similarly, delta VAB is equal to VA minus VB. And now I'm going to use VBC, delta VBC, that's equal to VB minus VC. So if I take that delta VBC and multiply it by C2, I also get the charge on the second capacitor, which is still Q. All right? So now take these two potentials here, these two, add them up. So delta VAB plus delta VBC. If you add them, what do you get? VA minus VB plus VB minus VC. These two cancel. And you get VA minus VC, which is delta VAC. All right, so in a series connection, the potentials add as long as you go along a single line only, okay? You don't want to branch off. There's no bifurcation. There's no forking, all right? It's just one line. There's always one line you can follow. You can actually add infinitely many capacitors like this all along a line, like pearls. You can line them up. It'll still be series connection, and then you can add those potential differences to come up with the greater potential difference, all right? So I'm going to use that. So delta VAC is equal to delta VAB plus delta VBC. Now, according to this equation here, delta VAB is nothing but Q divided by C1. And delta VBC is equal to Q divided by C2. That's the right-hand side. What about the left-hand side? Can I write this in terms of the charge and capacitance? But that capacitance will be what we call the equivalent capacitance of the system. All right. So what if I replace this system of C1 and C2 with a single capacitor? Will it have the same charge? So positive Q, negative Q, positive Q, negative Q. Can I obtain the same charge by using only one capacitor? Ideally, you should be able to. It may have a different D, different A, okay? But in principle, it should be possible. So I'm going to use that here now. That will be equal to Q divided by that. Okay, so if you get rid of the Q's now, the answer will be the formula for equivalent capacitance for a series combination. So 1 over C EQ will be equal to 1 over C1 plus 1 over C2. If you have more than one, more than two, keep adding them. 1 over C3, etc. Okay, that's how you find the equivalent capacitance of capacitors connected in series. Now, what if you connect them differently? Let's say this is your first capacitor with some surface area A1 and then separation D1. And you take another one here and connect that capacitor like this. And you can add many, 2, 3, 4, 5, as many as you want, like this. All right? This is what we call a parallel connection. Capacitors connected in parallel. So this could be A2, and this is maybe D2. Now, if these 2 points now are held at a potential, call it A and B, this is delta V, A, B. Because of this potential difference, we'll have a charge, or because we have charge on the capacitors, we have a potential difference between the plates. So let's mark those charges. The thing though now is that these charges don't have to be the same. So the positive charge is over here. This will be also positive. Maybe VA is greater than VB. That's why we would have positive charges on the left, and this will be negative. All right, now the amount of charge this capacitor can hold has nothing to do with the charge on the other capacitor. That charge only depends on the geometry of that capacitor, right? It depends on A1 and D1. So we have the capacitance for the first one, that is C1, which is equal to A1 epsilon 0 over D1, and then C2 is similarly A2 epsilon 0 over D2. So let's call the charge here Q1 then, and this will be equal to Q2. But I can always add these up, right? I mean, there's a physical connection between the two plates. Electrons are free to move from this one to that one, and once they reach equilibrium, they stop moving. So what do I have here? These two are connected. I have a total charge. Total charge, call it Q, or Q total, is equal to Q1 plus Q2. Okay? So charges add in this case. But both capacitors share the same potential difference. So there's nothing between this point and that point. So it's also A. This is A. This is B. This is B. There's nothing but just a wire, piece of wire, right? So if I write the charge on the first capacitor, which is Q1, and that will be equal to its capacitance, C1, times that potential difference, delta V, AB. And Q2 will be C2 times the same potential. If I add these two, Q1 plus Q2, I will get the total charge, Q. On the left, on the right-hand side, I will have C1 delta VAB plus C2 delta VAB. This is Q total on the left-hand side. Now, if it was possible to replace this system of two capacitors with one capacitor, which would hold the same charge, meaning Q total, okay, if this combination here could be replaced with a single capacitor, and it could hold the same charge, Q1, Q2, and then Q1 plus Q2 on the single capacitor. The capacitance here will be what we call C equivalent. So same potential difference times that CEQ will give me the total charge. That's the left-hand side. The right-hand side is the same. Let me just factor VAB out. So delta VAB, and those cancel. And I have the formula for the equivalent capacitance of capacitors connected in parallel. 2 or more, doesn't matter how many you have, okay? You can just keep adding them up like this. This will be the formula for the capacitors connected in parallel, okay? In parallel connection, charges add up. Voltages are the same. The potential differences are the same. And since charges add up, capacitances also add up. In the case of a series connection, what add up is the potential differences. What remains the same on each capacitor is the charge. All right? So you add the potentials, but the charges are the same. And the equivalent capacitance is found by that formula in the previous slide. But when you have a parallel connection, you simply add the capacitances. All right? And in electrical circuits, you will have many different combinations of these capacitors. For instance, what if you have 3 capacitors? C1 and C2, and then maybe a third one, C3, okay? So let's use numbers, okay? Let's say C1 is 2 nanofarads, and C2 is 3 nano. Nano means 10 to the negative 9. And C3 is 4 nanofarads. Okay, usually 1 farad is a really huge capacitance. Okay, in practical applications, it's picofarads, nanofarads, really small values. So, what will be the equivalent capacitance of this system? And if I held this at, let's say, 10 volts apart, what will be the charge on each capacitor? Q1, Q2, Q3. What are these charges? Okay, that's the problem. So find the charge on each capacitor. This is our problem. Okay, so the first thing you should do here for this problem, and many like this, this one, is to find the equivalent capacitance. Okay, so you replace this system with just a single capacitor and apply 10 volts to its terminals. You know, can you obtain the same charge? Now, the first thing you should notice that is actually, since you have a series connection between 1 and 2, the charges on each capacitor is the same. So Q1 is equal to Q2, right? These two will have to have the same charge. And Q3 can be added to that. So I'm just going to call it Q. If I add Q to Q3, this will give me the total charge in this system. All right. Okay, so let's find the equivalent capacitance for the capacitors in series, which are these two. Let's call this combination C prime. All right. So this is now my circuit. I have C prime here, and then I have this C3 connected in parallel. And this is held at 10 volts. All right. So what is C prime? Just use that formula. 1 over C prime is equal to 1 over C1 plus 1 over C2. Okay, 1 over C1, that is 1 over 2 nanofarads plus 1 divided by C2, 3 nanofarads. So that's equal to 3 plus 2, 5 over 6 nanofarads. So C prime is 6 divided by 5. What is it? 1.20, 1.25? 6 over 5 nanofarad. Okay, so now that I found C prime, how do I find the equivalent capacitance? This one, call it CEQ. CEQ will be simply C prime plus C3. So 6/5 plus 4. 26 over 5. 5 point something. All right. So that's the equivalent capacitance. How do you find the charges then? For Q3, you just multiply the capacitance C3 by the potential difference. So that is 4 nanofarads. These are in nanofarads. 4 nanofarads times 10 volts. That's Q3. And to find Q1, which is equal to Q2, you just subtract this from the total charge, and the total charge would be CEQ times 10. So 26 over 5 nanofarads times 10 volts. All right, so find Q total and subtract Q3 from it, and you'll find Q1, which is equal to Q2. Okay, so for most problems, that's your strategy. And in some cases, it may not work that easily. And but these are very rare situations, and I'll talk about them later, okay? So that's the circuitry. All right, let's talk about energy in capacitors. And I'm going to stop after that. So let's go back to our parallel plate capacitor, just a single capacitor. And you have charges here, positive charges and negative charges. all right, Q and negative Q. And these two are held D apart, and the surface area is A. And these 2 points now, call them A and B, have a potential difference, delta VAB, which is VA minus VB. And the electric field is delta V AB divided by D, and the capacitance is A epsilon 0 over D. And the charge will be equal to capacitance times delta V, all that stuff. Okay, now here's the thing though. Suppose I want to add more charges, all right? I want to add more charges to it. Now here's how you think about it. This is my electric field. If I wanted to take a negative charge from the left side, an electron, and bring it to the plate on the right-hand side, how much work would I do? You would be going along the electric field. You're taking a negative charge and bringing it closer to other negative charges. This negative charge don't want to be with the other ones, right? No, it will be attracted to the positive one. So you're pushing it close to that. So you're doing some work, all right? And how much work would you do and all that? So here's the deal. This charge here, Q is equal to C times delta V, all right? Now C has to do with the dimensions, right? C doesn't change with charge or anything. Delta V, on the other hand, yes, it changes, right? Delta V depends on the electric field. If you add more charge, the electric field will go up, and then the potential will increase as well. So every time you add a charge, you're actually increasing the potential. Therefore, it's going to get even harder to make that move, right? So if you, let's say you're here, Q, you go from Q to Q plus DQ, right? I mean, I said just move one electron, but infinitesimal charge, same idea. So you're increasing the potential this way. Okay, so let's find the infinitesimal work you do to do that. All right, so each time you add the charge, you're increasing the potential as well. So if I divide this by C, all right, Q over C. See, what is work? Work is energy, right? And energy is potential difference times charge. So this is where I'm getting it from. So work, energy. Remember how energy was defined as Q, some test charge, times VA minus VB from previous chapter, right? So basically, this potential difference is multiplied by the charge, all right? So divide the charge by C, you get the work. If I integrate this, for all charges that are present, some total charge from 0 to total charge Q, I will get the total work, which will be total energy stored in that capacitor. Total energy. So Q dQ will be 1 over 2 Q squared over C. If you plug in the limit from 0 to Q, you will get Q squared over 2C. Let's call this U. U for energy, all right? So this will be actually like a potential energy stored in the capacitor. So I'm going to put an E here. The energy stored in an electric field, Q squared over 2C. Now using this relationship here, I could write it as C squared delta V squared divided by 2C. In other words, 1/2 C delta V squared. That's another expression for U. Or I could get rid of C, just use Q and V. So Q squared over 2C would be equal to Q squared divided by 2. Instead of C, I'm going to write Q over delta V. So 1/2, one of the Q's cancel, delta V times Q. All right, that's also U. Here you have 3 different versions of the same formula, energy. Q squared over 2C, or 1/2 C V squared, or 1/2 Q delta V. All right, so this will be the energy. Let me stop here. In the next video, I'm going to talk about the electrics, and pretty much we'll be done. Oh, by the way, since that's energy, we can define an energy density. All right, so the space inside or between the plates, it has a volume, right? That volume is equal to, like a cylinder, or any actually prism would work, is equal to A times D. So if I divide the total energy by this volume, I'll get energy per volume. All right, that would be the energy density. Little u. Little u will be capital U divided by the volume, AD. All right, so let's find an expression for this in terms of electric field. So I have here, we can use any of these 3. Which one do I want to use? Let's use, I don't know, let's use the last one, 1/2 Q delta V divided by AD. Okay, the presence of AD there, actually, I'm going to use this. Let's see if I can, no, actually I can use this one. I can replace delta V by E times D. So I will have here 1/2 Q times, instead of delta V, I'm going to write E times D divided by AD. So I will get rid of these. All right, let's move one more step ahead. Now the electric field between the plates is sigma over epsilon 0. And sigma is the charge density, which means Q divided by A. So I'm going to plug this in here. So let's simplify. 1/2 Q over A times E. Is that what I want to do? I want to get rid of Q, actually. I want to get rid of Q. So let me replace Q over A. Let me do it the other way around. Let me replace Q over A with epsilon 0 times E. So this here, Q over A is also here, right? That's equal to, oops, that's equal to epsilon 0 times E. And there's another E here, which makes it E squared, okay? So this will be the energy density. 1/2 epsilon 0 E squared. That's a very important result. And maybe you're already guessing it's actually more general than capacitors, right? Because there's no A, there's no D there. It only depends on the permittivity of the free space and the electric field there, okay? Right now in this room, there's electric fields. All these radio towers and mobile phone towers, TV signals, well, cable TV, but anyways, radio signals, let's say, lots of electric fields. And we have that constant. So just find the electric field, just find the energy density, you know, in a given area. There may not be any capacitors, right? It's a generic result. So this is the electric field. When we do magnetism, we're going to have something like this as well, okay? Energy stored in magnetic fields. This is only electric field. Okay, so this is the electric field, I'm sorry, electrical energy density. Energy density. If you multiply it by a volume, you get the total energy. All right, I'm going to stop here. And then in the next video, I'm going to talk about dielectrics. So those are used to increase the capacitance. What you do is you take your parallel plates and place a non-conducting material between them, and your C changes and it increases. That's why these are used in the first place. So I'm going to talk about this in the next video, and after that we'll be finishing the chapter. It's almost the end of it. All right, so let me stop here.